Hello, so welcome back to the afternoon session. So we have two more talks lined up in this session. The first speaker will be Shaun Seaman. Excuse me. Shaun is a senior statistician at the MRC Biostatistics unit. His research methods include methodology for drawing causal inferences from observational data and for handling selection biases and missing data, and he is particularly interested in the application of modern data adaptive methods to causal inference problems. So Shaun is going to be speaking about nowcasting COVID-19 deaths in England by age and region. Shaun.
Thank you very much. Good afternoon, everyone. Here it is. So this is joint work with Pantelis, Megan and Daniela. And I'll start with some background. So in the UK, the first case of COVID was reported at the end of January 2020, and the first death was announced at the beginning of March. And the government's response to the epidemic was informed by a number of epidemiological indicators. An important one of these was the number of deaths that were occurring. And this was crucial to monitoring the burden of COVID and informing methods which were attempting to predict the epidemic. And the problem was that the information that were available on the numbers of deaths was affected by reporting delays. Typically, several days pass between a death occurring and being reported to the public health authorities. And this reporting delay can be quite a lot longer than that. A consequence of this was that in the first wave in 2020, the day on which the most deaths occurred in England was the 9th of April, but the day on which the most deaths were announced, or reported I should say, was the 22nd of April, so almost 2 weeks later. And these reporting delays obviously mean that there's uncertainty about the number of deaths that occurred in the most recent days, and so uncertainty about recent trends. And the task of estimating the number of deaths that have occurred so far on each day in the past, using the data that are available up until now, is called nowcasting. So it's like forecasting, but it's about now and the immediate past rather than the future. Now, back in April 2020, we were given the task of producing nowcasts separately for each of 7 regions of England and also separately for 5 age strata in each region. So ranging from the under 45s to the over 75s. And for this task, we had data on lab confirmed COVID deaths, so deaths in people with lab-confirmed COVID infections, reported by NHS hospitals, the Demographic Batch Service, and health protection teams. And for each reported death, we had the date of death, the date of the report, the age of the deceased, and the region in which they died. And to illustrate this talk, I'm going to use data that were available up until the 29th of June. And by that date, there had been about 38,000 deaths reported. So this graph shows the data. You can see the number of deaths that occurred on each day from the 22nd of March until the 29th of June. You can see that, as I mentioned, the peak is on the 9th of April. And you can also see that in the last 3 days, 27 to the 29th of June, the number of deaths is very low compared to what it had been a few days before. And that's not because there was a sudden precipitous decline in the number of deaths. It's simply because deaths that occurred on these last 3 days in particular, a lot of them haven't yet been reported. This graph shows the same data, but now the deaths are arranged by the date on which the report of the death was made. You can see now that the peak is on the 22nd of April, as I mentioned, And you can also see that the number of reports varies tremendously from day to day, and it tends to be lower at the on Sundays and Mondays, which I'll refer to as the weekend just for convenience. And the weekend reports are marked by crosses. But even within a Tuesday to Saturday period, the number of deaths can vary a lot. And there's an example that Tuesday, the 26th of May, when the number was particularly low. Okay, now here is a simple estimate of the delay distribution. The delay, remember, is the time from a death occurring to its being reported. And we've got a different estimate for each of the 5 age strata. This is using data from the whole of England. So the black line, that represents the over 75s. And you can see that, for example, we estimate that about 25% of deaths are reported within a day, about 40% within 2 days, 60% within 2 days, I meant to say. And about 85% within a week, and then almost all of them within 2 weeks, but not all of them. You can also see that the delay distribution the delays tend to be longer in the under 45s, that's the red line. And perhaps they also tend to be a bit longer in the over 75s, the black line, and they're pretty similar in the other 3 age strata. Now this estimate was produced using a method published in 1990 by Brookmeyer and Liao. It's a very simple method, and it assumes that the delay distribution doesn't depend on the day on which the death occurred. Okay, now we could use that estimate to produce a nowcast. So the way that would work is we'd look at the number of deaths, say, that occurred in the over 75s on the 27th of June. There were 9 of them. We look back at our estimate. I said that about 60% of deaths in that stratum are reported within 2 days. So we'd simply take our 9 observed deaths, divide by 60%, and that would give us an estimate of 15. So 6 deaths haven't yet been reported. Now, there are 2 problems with this very simple method of estimating numbers of deaths. The first is that the delays may well depend on the day on which the death occurred. So delays may get longer or shorter over calendar time, and almost certainly depend on the day of the week on which the person died. Second problem is that this estimate for the 27th of June is 15. I haven't used any information on deaths that occurred on other days which were nearby, like the 26th of June or the 28th of June. And we probably believe that the number of deaths is changing gradually over time, and we're not making use of that information. So we looked around in the literature to see what more modern methods were available, and fortunately discovered a method proposed by Stoner and Economou. This method has, it's a Bayesian method, and it has many advantages. So it allows for flexible modeling of changes in the reporting delay distribution. It accounts for over-dispersion in the numbers of reports per day. I'll say a little bit more about that later. It also models the number of deaths occurring per day as a smooth function of time. And so that means that our estimate for the 27th of June will be informed by information about the 26th of June, the 28th of June, and so on. It's a hierarchical model, which means that information about the numbers of deaths occurring and the delay distribution in one age stratum will feed in to our estimates of those quantities for other age strata. So there'll be some borrowing of information between age strata. And because it's a Bayesian method, our nowcasting estimates have associated uncertainty, which we are quantifying in terms of Bayesian posterior credible intervals. Okay, now I really like this method, but nevertheless, we made several modifications to it. We modeled the day of the week reporting effect in what I think is a more realistic fashion for the COVID data. We included random effects, reporting delay specific random effects to account for a certain type of correlation between the reports that the original model wasn't accounting for. We also modified the Markov chain Monte Carlo algorithm used to fit this model in order to improve the mixing of the Markov chain and so reduce the computation time. And we also developed a computationally efficient way to constrain the delay distribution to be the same in either all of the age strata or some of the age strata. And this is useful because, as I hinted earlier on, we think that the delay distribution is probably the same in the 3 middle age strata, only being different in the oldest and the youngest age strata. Okay, so I'm now going to describe the model. I'm not going to give you all the details, but I'm going to try to give you a flavor of what it looks like. So some notation then. Day 0 is going to be the first day from which we're using reported deaths. So in this presentation, that's going to be the 22nd of March, 2020. Day capital T is the day on which we're actually carrying out the nowcast. So it's the last day for which we have reports of deaths available, and that's the 29th of June. And we're going to restrict to deaths which are reported within 42 days. Okay, this we think is reasonable because the data very much suggests that the vast majority of deaths, the vast majority of deaths are reported within 6 weeks. And a bit of important notation which I'll be using. So ZTD is going to denote the number of deaths that occur on day T and that are reported with a delay of D days. So these are deaths that are reported on day T plus D. And YT is the total number of deaths that occurred on day T. So that's just the sum over the corresponding ZTDs. Now we're stratifying on age group, so really these variables should be indexed by stratum, but for simplicity I won't bother doing that here. Okay, now some of the ZTDs are observed and some of them are missing, and some of the YTs are observed and some of them are missing. And the nowcasting task is to estimate the missing YTs. And in a moment I'm going to show you a diagram which just indicates which of the Zs and which of the Ys are missing and which are observed. So on day 0, which is the 22nd of March, this is more than 42 days before day capital T, the 29th of June. And so we know about all the deaths which are reported within 42 days of that day. So I've got these ticks. All those ZTDs are observed. And consequently, YT is also observed. Now, the same is true of day 1, and so on, day 2, right up to 42 days before the 29th of June. But 41 days before the 29th of June, we haven't yet observed the deaths which will be reported 42 days after the 19th of May, which is the 30th of June. We're not yet there. So this ZTD is missing, and consequently, although we've got a lot of information about YT, we don't actually know exactly what YT is. And the same carries on until we get to 29th of June itself, and then we don't know any of the ZTDs because these are all deaths which are reported on the 30th of June or later on instead. So what we're trying to do then is estimate these YTs. That's nowcasting. And the ZTDs and the YTs are all random variables in this Bayesian model, and so we're going to be sampling from these random variables. Okay, now the Bayesian model is composed of 2 parts. There's a submodel for the numbers of deaths that occur on each day, that's the YTs. And then there's a submodel for how those YT deaths that occurred on day T, how the reports of those deaths are distributed over the subsequent 42 days. So that's a model for the YTDs given the YT. Right, so I'll describe the first of those two models. So this assumes that the YTs have a negative binomial distribution with some unknown mean lambda and variance lambda times 1 plus theta. Now, if theta's unknown, I'm going to estimate it from the data. If theta is 0, then this is just a Poisson distribution. Otherwise, theta measures the amount of over-dispersion. And we're assuming that these expected numbers of deaths, they change or evolve smoothly over time. And specifically, the way we do this is to use cubic spline. So we assume that these lambdas are equal to the sum of 2 cubic splines, one which is specific to the particular age stratum that we're looking at, and one which is common to all the age strata. And by doing so, it's a hierarchical model, and by doing this, we allow the trajectory of deaths to be different in all of the age strata, but we allow for the possibility, which is quite likely, that those trajectories are all going to look fairly similar. Okay, now on to the second model, which is how the reports of those deaths are distributed over the 42 days after they occur. So PTD is going to be the probability that a death on day T has a delay of D, and the model assumes that conditional on those probabilities and the number of deaths that occurred on day T, these counts of the reports over the subsequent 42 days has a multinomial distribution. Now, we could model these PTDs directly as a function of calendar time T, day of death, and the delay D. We could do that, and that would then allow us to model changes over calendar time in the delay distribution and reporting day effects. But even after accounting for these systematic effects of calendar time and reporting day, the ZTs, the ZTDs, might be over-dispersed compared to a multinomial distribution, just because there's some extra variation that we're not accounting for, short-term variation. And Stoner and Economou, who developed this method in the first place, they showed that if you don't account for that over-dispersion, the result is that you overestimate the extent of extra Poisson variation in the YTs. That is, you overestimate this theta here, the dispersion parameter, and the consequence of that is that you get unnecessarily imprecise estimates of these missing YTs, these things that you're trying to nowcast. So we don't want to do that. So instead, the model incorporates an extra layer. So these PTDs, probabilities of reports on a particular day, they are assumed to come from a distribution, a generalized distribution, generalized Dirichlet distribution. And this is an extension of the Dirichlet distribution, which is more flexible, and it allows, for example, for positive correlations between these probabilities. The Dirichlet distribution always assumes that that correlation is negative. So the important thing is it's just a more flexible distribution to use. And we can interpret the parameters of this generalized Dirichlet, which are the V's, VTDs, and the phi's. The VTDs, or VTD, is the expected hazard of reporting on day D after the death occurs. So it's the expectation of the probability that a death that occurs on day T has a delay of D days, given that it has a delay of at least D days. And then the phi's, less importantly, the phi's reflect the, or measure the amount of variation in these hazards. And then rather than modeling the PTDs as functions of T and D, we model the VTDs. And I'm not going into details here, but there's a hierarchical structure on the VTDs as well, which allows for borrowing of information between the different age strata. So we learn about the delay distribution in one age stratum from using information also on the other age strata, because they're likely to be somewhat similar, although they may be a bit different. A nice feature of this model is that you can integrate out the PTDs analytically and get a closed form for the Zs given the Ys and the Vs and the Phis. And that's nice because it makes fitting this model by MCMC much more feasible. The mixing would be terrible if you didn't do this. Okay, so here are some example results. So this is for the whole of England in the oldest age group. The broken line shows the number of deaths that had been reported, that occurred on each day and had been reported by the 29th of June. The solid black line, that shows the posterior mean for the number of deaths, the YTs. And so you can see, for example, that the observed number of deaths is 9, and our estimate is about 64. The shaded area, which I now see you can barely see at all, actually, that shows the 95% posterior credible interval. And the purple line, well, 42 days after this nowcast was conducted, we know the truth. Okay, we know because all those deaths reported within 42 days, by 42 days after the 29th of June, we know about them all. So the purple line shows the true numbers of deaths that occurred on each day. And we'd hope the black line will be somewhat like the purple line. We'd also hope that about 95% of this purple line would lie within the posterior credible interval. It's difficult to see on this slide, I know, but actually just over 90% of it lies within the credible interval. So that's fairly good. Here, just to illustrate, we've got results for another age stratum, younger people, where there are fewer deaths because fewer people die of COVID when they're younger. And here are results for just one of the 7 regions, which is London. So again, the numbers of deaths are smaller because it's just one region. Okay, now, as I said, 42 days after the nowcast is carried out, we know the truth. And so we can retrospectively compare our nowcasts with the truth and see how well they performed. And so we did this. So we took data over a 9-month period from the end of June to the end of March 2021. And every 5 days, so that's the 29th of June, the 4th of July, the 9th of July, and so on, we carried out nowcasts. We did this for the whole of England, and so over the 9-month period, this gave us 56 nowcasts, and we did it in each of the 7 regions, so we got 392 nowcasts. And then for a nowcast that was carried out on a particular day, did T, so for example, the 29th of June or the 4th of July, we looked at each of the previous 7 days, and we calculated the difference between our estimates or posterior mean of the number of days that occurred on that, number of deaths that occurred on that day, and the true number that occurred on that day. And I'm going to refer to that as I'm going to refer to the average difference as the bias. Not quite correct, but that's what I'll call it. And we also noted whether the posterior credible interval included the truth, and so I'll call the coverage the proportion of times that the credible interval included the truth. So we want the coverage to be about 95%, and we want the bias to be close to 0 because we want the nowcast on average neither to be too high, that would be positive bias, nor too low, negative bias. And here are the results. So the top table is for England and the bottom is for the 7 regions. And we've got 5 rows, 1 for each age stratum. And on the left-hand side of the table, we've got the bias, on the right, the coverage. Now you can see, this is for nowcasts of 1 day earlier than the nowcast is made. This is 2 or 3 days. I'm averaging over those 2 or 3 days. This is 4 or 5 days, and this is 6 or 7 days. You can see that all of these numbers, they're round about 0, so that's good. It's difficult to know whether 1.16 is a large number or not, and that's why I've put the blue column in there. So the blue column shows the average number of deaths that occurred per day in these 5 age strata. So that places these numbers in context. On the right-hand side, we've got the coverage, and you can see that in the 2 youngest age strata, first 2 rows, the coverage ranges from 95% up to 98%. So perhaps it's a bit bigger than we want it to be. We want it to be 95%. And in the 2 oldest strata, the numbers vary from 94% down to 88%. So that's a bit lower than we want. Now, I acknowledge that 88% is not 95%, but I still think it's pretty good. It's not far off. And I want to explain why we think these numbers for the younger strata are more than 95%. I think it's because of discreteness in the data. So for quite a lot of these days, particularly in the younger strata where there weren't that many deaths, there are a lot of days on which there were actually only 0 or 1 deaths. And in fact, the red column shows the percentage of days on which the true number of deaths was either 0 or 1. So it's more than half in the youngest age stratum. Now, when the true number of deaths is 0 or 1, it's quite likely that the 95% credible interval will go from 0 to 1, or even from 0 to 0. And in that case, it's also quite likely that the 95% credible interval will also go just from 0 to 1 or 0 to 0. So the 95% and the 99% credible intervals will often be the same. So it's hardly surprising if the coverage of the 95% credible interval is greater than 95%. And in the regions, let's look at the regions now. Well, again, the bias is small compared to the average number of deaths that occurred per day. So that's good. And the coverage is, well, they're all above 95%. And that's because, as I explained, that's because of the discreteness, because now we've got lots and lots of days on which the number of deaths is very, very low. Okay, so in conclusion, I've presented a new model for nowcasting deaths in COVID individuals with COVID. It's based on the original model of Stoner and Economou, but we've made quite a lot of modifications to it to make it more suitable for the COVID data. The model allows for flexible, realistic modeling of the delay distribution, and it also quantifies the uncertainty in the nowcasts in the form of credible intervals. And our retrospective evaluation suggests that the coverage of these credible intervals is pretty good. Now, for well over a year, Pantelis was applying this method once or twice a week and producing nowcasts and then sending them to SPI-M and Public Health England's joint modelling team and to the Joint Biosecurity Centre. So there was quite some demand for these nowcasts. And I'll just finish by saying that we're producing these nowcasts. Just using data on deaths. And it would be interesting, and potentially it would improve the precision of those nowcasts if we used information on earlier outcomes that occur earlier than death, such as the numbers of patients who are in intensive care on that particular day, and possibly even the number of people who are testing positive with COVID. Okay, that's all I have to say. Thank you very much for your attention.
Thank you, Shaun. Have we got any questions from the room?
Sheila first. Yeah. Are you ready to catch Sheila?
Sorry, Linda. Shaun, I'm assuming that those were all deaths in England, not just the hospitalised deaths that you were analysing.
These are all deaths, so they reported by NHS trusts, by public health teams, by the DBS, the Demographics Batch Service. And then, I didn't say it, but later on in the epidemic, we started using ONS data as well.
Because the earliest death in the United Kingdom was, I can't quite remember whether it was the 30th or the 31st of January, but it wasn't reported by the Office for National Statistics until September of 2020, when the family asked for the post-mortem results to be reviewed, because the father, who'd become ill post-Christmas and had had a post-mortem and X-ray, and on review of the post-mortem, the X-ray of the lung showed the classic COVID picture, but of course it wasn't recognised as classic in January 2020 when he died. Interesting.
So, so on the death certificate, it originally didn't mention COVID, and then it was reviewed.
Oh. And the post-mortem was done because of astute clinicians who didn't understand why this elderly gentleman was not responding to treatment of his pneumonia. And they thought perhaps he had an occupational disease like asbestosis, which gave a reason to do a post-mortem.
Yeah, yeah.
I'm not going to throw from that apart.
Hi.
Hello.
So if I understand correctly, when you have very rare events like 1 or 2 deaths a day, your model kind of doesn't work very well because you're discretizing. Did you think about perhaps?
Well, I'm not sure whether it didn't work very well. I mean, it nowcasts that 0 or 1 deaths occurred and 0 or 1 deaths occurred, so it's getting it right.
Yes, but it's kind of like I would get it right randomly too, because the events are so low, right?
That's fair enough, yeah.
So you're not doing well, you're just lucky. Did you think about grouping them perhaps per week?
The thing about per week is that you then have to wait longer before you see whether there's a rise. And what's important is to detect rises in the numbers of deaths that are occurring. So we didn't do that. Yeah, that's all I can say, really.
So just because the pandemic had, periods in which everything was accelerating and then periods in which everything was quiet. So I thought perhaps adjusting your timelines might reflect that. You need to be much quicker when things are going exponential and not so quick.
Yes, well, I suppose we developed the method to cope with the times when it was really needed.
Yeah.
And then we just, why bother adapting it for the times when it's not really needed? Mm-hmm. So there were I think there were 2 waves during that 9-month period and then in the middle of that 9-month period, there was just a long spell where there wasn't much going on.
Thank you.
Will. Sorry, I'll just see Oscar's hand.
Thanks, yeah. Just a kind of related question to that. And I was wondering why your interest is in estimating the count, YT, rather than the underlying rate, which I think you'd called lambda.
Well, because I suppose there are several answers to that question. Firstly, the lambda t is more abstract. The YTs are deaths that are really happening. The lambda t is more of just a way of using information from one day to inform the number of deaths that probably occurred on a different day as well. So the lambda t's, or that part of the model, is imposing a smoothness assumption. It's saying that the number of deaths per day is probably changing gradually over time. And so we gain some information from that assumption. But the lambda t's themselves are not particularly interesting. We're not trying to forecast deaths. We're trying to nowcast deaths. We leave the forecasting to other people. So if the lambdas are if the lambda's shooting up steeply, then yeah, you could forecast if you wanted to. You could continue that trend and then even sample numbers of deaths that are implied by, well, not implied, but suggested by that particular lambda in the future. Could do that, but we left the forecasting to other people.
So what's the nowcasting actually? What's the utility of the nowcasting? Maybe that's...
So the nowcasting, well, first of all, the government was making decisions about whether to impose lockdowns or other measures. And it was informing those decisions by the numbers of cases that were being reported, the number of deaths that were occurring, how busy the hospitals were. So that was part of it. And part of it was that the forecasters, they could have built nowcasting into their forecasting models, but quite a few of them didn't do that. They just took they took nowcasts from this or some other method and then plugged them into their forecasting models.
Right, okay. So they needed the kind of data, raw data.
So they needed the corrected data, as it were. Yeah. Corrected for reporting delay.
We have one question on. Yeah, so Ben Swallow, you have your hand raised. Can you please unmute and say your question?
Yeah, certainly, thank you. I just wanted to pick up on the point you made at the end, Shaun, about combining other data streams into the nowcasting, such as hospitalizations and positive tests and things. And I guess the difficulty there, we've looked at some of this and combining time series for nowcasting, and the difficulty is knowing what the relative length of time the delay in reporting is relative to the amount of time it takes people to get or move from one compartment to the other, and whether that amount of time changes over the course of the pandemic. So I was just wondering if you had any ideas about how that might be incorporated into this Bayesian approach. Thank you.
Well,
can you repeat the question?
Yes, it was really noisy. Okay, so as I understood it, the question was, I didn't get all the details. The question was about do I have any ideas about how to incorporate information on numbers of patients who are in intensive care or numbers of people who are testing positive. Is that fair enough, Ben?
Yes, it is. Thank you. Yes.
Okay. So I haven't given that a huge amount of thought, I must admit. One simple thing you could do, but you could probably do something better than this, but one simple thing you could do is go back to this part of the model, which is the model for the total numbers of deaths that are occurring on each day. And this is assumed to be negative binomial with a mean of lambda t, and then the lambda t's are assumed to follow cubic splines. Well, you could include as a sort of covariate in the model for lambda t. You could have your cubic splines, but you could also have a covariate, which is in some sense the number of patients in intensive care 10 days earlier or whatever it is, something like that. So that's where I'd start looking for a solution, I think. But that's probably far from the optimal solution.
Great, thank you.
So in the interest of time, we should move on, but let's thank Shaun again.